back, everyone, to Office Hours Unplugged, where we chat with the most prominent researchers and PIs here at McMaster. Today, we have our very first mathematics professor coming into the studio, Dr. Blaise Bourdin. Would you please introduce yourself to the audience and let them know a little bit about yourself and what you do here?
Yeah, hi. So my name is Blaise Bourdin. I'm indeed a professor in the math department. And so I grew up in France, was educated in France, traveled a little bit through Denmark, the United States, and moved to Mac in 2021. And I'm an applied mathematician. I mostly study problems that are halfway between mathematics and solid mechanics or application to engineering. So fairly concrete and tangible application for a mathematician.
Yeah. And how did your journey through academia sort of start? I mean, take me back to your bachelor's.
So as a kid, I was really first. I always loved math. I was good at it. Maybe that's why I loved it. And I had this abstract idea that I wanted to do research in mathematics. I had no idea what it meant. I just knew that there were people who were paid to do mathematics all day, and I thought it was a really cool job. I went to a kind of a smaller school outside of Paris, and didn't know exactly what I wanted to do, but I always took the classes that had the most math and so on. And at some point, I had a professor who kind of took me aside, and he probably felt that I was good at what I was doing, but also that I was interested in continuing. And so really laid the ground. So if indeed you want to do research in mathematics, this is how it works. You know, do a master's and do a PhD. But if you want to do a master's that will lead you to a PhD, these would be the good masters to go to. This would be the good classes to take to. So really helped me preparing myself. And then it's a long process. It takes. So we always think about the PhD as being the gateway to research and to academia, but you also have to count a couple of years of postdocs. So I think I got my first faculty position at age 31, which is fairly standard in math. You know, in many areas of science, it tends to be later.
Yeah, it tends to be much later.
Yeah.
Yeah.
It's a, you know, it can be a bit difficult. It takes a lot of time, and by the time you finally get a stable position, all your friends have been married with kids and have a real life for a long time. And yeah.
And would you say that that you mentioned a professor that kind of guided you towards mathematics? Would you say that person's been sort of like your mentor or the person you looked up to or tried to emulate in your journey?
So I wouldn't say that he really was a mentor in the sense that we never interacted so much beside the a few classes, but definitely he was somebody. Jean-Claude Guillot was his name, who had a really strong impact on my career. And as a matter of fact, I know other people who are exactly in the same situation, didn't know exactly what to do, and talked to him and got a much better idea. So I'm very grateful, and also I try to keep that in mind. Is that we can even simple interaction with students can be meaningful. Yeah, I think it's also a great part of the job.
Yeah. And what drove you to do the specific kind of research within mathematics that you do?
So I think as a first or second year student, as many mathematicians, I was really interested in the romantic aspect of very pure and far from reality and really out there. But at the same time, I like to tinker with stuff, and I like to build things and so on. And so when I took classes first in numerical analysis. So numerical analysis is the field of mathematics that deals with finding a way to solve problem using computers. So compute the solution of a specific equation. And I really thought that it was great because it started combining two of my passions. Is that you could do the math, you could do everything that is mathy related, understand structures and so on, and then have the direct connection with other stuff that I liked. So that's how I went into applied mathematics in general.
Yeah, and would you say that sort of being able to apply just the pure mathematics into an actual practical application that has maybe like brought you more meaning in the math that you do, or
so look, everybody is different, and I don't mean that as a judgment. I'm really interested in the math that allow me to understand the real world. I know it sounds kind of counterintuitive sometimes, but mathematics is about concept, structure, interaction between concepts. What we're really good at mathematicians is drawing these connections. And the concept can be completely abstract, but they can also be a formalization of reality. So, so I think my personal taste is I usually don't ask myself a lot of questions that are really, really theoretical. Just understand mathematics for the sake of mathematics.
Yeah.
But I see things around me all the time that I'm like to understand, and sometimes they translate into some mathematics, and that I'm interested in the mathematics.
That's interesting. And just kind of zooming out a little bit, did the research that you did in your master's going into your PhD and then your postdoc years, how did that kind of differ from each stage of education? How did that evolve, sort of?
So there's been a real continuity, is that there are themes of my work that I studied in my PhD that I still follow. I developed a computational method to study the evolution of cracks in material. And I was part of really the genesis of this type of approach, wrote the first numerical simulation codes and so on, spent many years trying to convince the world that it was a good idea. I think people are convinced now that it's a good idea, and I still work on that. And then occasionally I see other side project or side application of the same framework. But my mathematical journey has been really focused on applications of mathematics to mechanics, to materials, to structure, engineering problems, and so on. So there's real continuity.
And what would you say, given that a large part of your education was in France, how did that sort of differ when you later got a faculty position in Louisiana? We were talking about that earlier. How did that sort of differ from going from France to Louisiana and then back to McMaster here?
Yeah, it's interesting because it's so first there's something really challenging in teaching in a system you were not educated in, and it used to constantly bite me in the US, and essentially I got used to it, and it came back when I moved to Canada. There are things that I'm expecting that students have studied and that they haven't, and conversely. Also, some of the some courses, some coursework I've never taken. So I remember the first time I had to teach a differential equation class in the US, and it's actually fairly similar to the way they're taught here. So I look at the outline and say, oh yeah, I know all that stuff. And comes week 3, I open my book and I try to start preparing classes a little bit in advance. And I realized that I had never studied any of the material that I was supposed to teach. So, okay, I mean, you survive. You try to be a little bit ahead of the students. But what I remember, there was lots of formula to memorize, and I'm really not good at that. So I had to find ways around that.
Yeah.
So.
And how did you sort of mold your teaching style to complement that?
Oh, so yeah, that's another difficult part. Is you have to really understand the culture.
Yeah.
And the role of a professor, the nature of interaction between professor and student, can be very, very different in various countries. So in France, the concept that you could call your professor by their first name is just absolutely inconceivable.
Yeah.
We have the tu and the vous, the polite versus the formal, informal versus formal form, and it's always form, sir, ma'am, and so on. And conversely, as a teacher, you're at the same time much more respectful. You also use the formal form with your students.
Yeah.
But at the same time, we tend to be a bit abrasive. Yeah. I've been told by students that I can be abrasive. So,
I can imagine the cultural whiplash going from France to in the middle of Louisiana and then all the way over to Canada. That's a very
yeah. But it's. I think that's a really interesting part of the job. And here also dealing with. I still trying to wrap my mind around the Canadian culture, population, and so on. But there is this combination of homogeneity and extreme diversity, which is I find that very challenging, but in a good way. To what extent is it appropriate to make fun of somebody or just joke with somebody in a class? It's never. I never have any ill intent, but maybe sometimes.
Fair enough. and so you were in Louisiana State University up until what year?
2021.
Yeah, and then you came to McMaster right after that, right?
Yeah.
What kind of motivated that change, given that you were there for quite a while?
So I want to say midlife crisis, but that's a bit more complicated than that.
Yeah.
No, I had been in the same position for almost 20 years, and it was very comfortable. But I thought that if I wanted to do something challenging, the window of opportunity was closing. For many reasons. Some as simple as simply being able to move at a point where you're not going to completely rake your chances of having any type of retirement, or just still having the energy to move.
Yeah.
And living in the hot, humid South, I had been vacationing in Canada for a couple of years because the concept of getting anywhere warmer during the summer was pretty unappealing. So what I had seen of Canada, I really, really enjoyed. I realized that I really did not understand the Canadian society. But so that part, I was really interested by just the culture and the quality of life coming to Canada. And then in 21, so during the pandemic, the math department opened a senior position. So it's also not always really easy to move or to switch position as a senior person. But I thought it was a great opportunity. I applied and
worked out.
Yeah, it worked out well.
And just kind of zooming out a little bit, just to discuss your research. What was the original vision for your lab when you started out?
That's a tricky question. I think you make it sound like I really have a big vision and great plans and so on. And I mean, a little bit of this is true, but a lot of it is also opportunities. And so first, in mathematics, we don't have labs in a sense of experimental science and so on. Just have tables, papers, and pencil, and sometimes computers. And so it's not like we have to fill specific position at specific times because there are real needs for somebody who does this type of experiments and somebody who does that and so on. So usually have a bunch of problems that I'm interested in. I try to keep a couple, and then depending on what students are looking for position, postdocs, and what the funding scene looks like, I try to adapt myself. And also collaborative opportunities. So, for instance, I worked a lot with the people in geology, petroleum and chemical engineering back when I was at Louisiana State. Kind of by accident, because it turned out that they had problems which I thought I could solve, and we got along and started working together. But yeah, so I don't want to pretend that I have grand plans and a grand multi-year strategy. I don't play three-dimensional chess.
Fair enough.
It's
you would say it's more so like opportunistic. You just see like a project you're interested in or a collaboration that you like, and you just take up the collaboration.
Yeah, and opportunistic, not in a good way. Leverage skills and opportunities. Yeah,
that's actually a very interesting way of going about it. I've never really thought of that kind of angle, and I can see how it could be very rewarding or refreshing to be able to just on a whim just chase what you're interested in specifically.
Yeah. I think that's the fact that we don't need a huge experimental infrastructure gives us a lot of flexibility. And flexibility and also freedom and makes I would feel really stressed out if I had to manage a whole group of
like
people.
A box. Fair enough. And were there any challenges that you encountered in the initial setting up of your research group and all of that?
So two different ways. So first, so here coming to Mac, the beginning was difficult. Just recruiting a student was more difficult than I thought. And particularly because if you don't really have a local network of colleagues, you know what you do and who are going to refer good students and so on, it makes life a bit more difficult. Simply understanding the tradition, understanding how to read a file. Here people are very focused on grades. I tend not to. So try to make my idea of what is a student like based on a file or on a quick discussion when you interview students. So that was a bit difficult. But the rest, no, just do what you enjoy and.
Would you say just being in uncharted territory, not really being that well connected, in the beginning at least, was kind of, as you said, that was like the major hurdle for you, right?
Yeah. Plus, I moved right during the pandemic.
Oh my God!
Actually, I never interviewed in person. I got a Zoom interview and I took the job sight unseen.
Oh my God!
Sold my house. We put the dogs in the car, and my wife and I drove north.
Oh well. And I guess just to sort of zoom out a little bit, your lab is very interdisciplinary in what it does, so to speak. And is there any project or collaboration that you are specifically, I guess, stoked about that you'd like to maybe mention?
Okay, let me think for a second. So it's not completely fully defined. We're still trying to shape it. But so I've done a lot of work over the year on a field called optimal design. And so optimal design, um, the idea is okay. So I'm gonna have sorry. It's gonna
Yeah.
do some background and so on.
Yes.
So a lot of what you do in engineering or in computing is solve an equation. So for instance, you have a beam and you try to figure out is it going to bend or not. Or,
Yeah.
so we call that a direct problem. You formulate the problem and you try to compute the solution. Then you also have inverse problems. So you try to formulate a problem knowing your solution. And so optimal design is exactly something like that. So design the geometry of a mechanical part so that it's optimal in some sense. So it's a stiffer, so it has a higher natural frequency, or it's a lighter for a certain resistance and so on. And so one project that I had a couple of years ago was what we called optimal design of responsive structure. And so the idea was to build a structure that are made of regular passive materials and active materials. So think something that can a material that has a high thermal expansion coefficient.
Uh-huh.
And so by simply playing with the fact that one material deforms and the other doesn't, you can create structure that really change shape and that morph.
Mm-hmm.
And so we did this project where we're trying to design a structure that had specific properties. So that was with my student Jamal, who's graduated 2 years ago. One thing that he did is kind of if you want a compliant robotic arm. So
Yes.
depending on how you would apply some temperature field, you will have a part that moves left and right or up and down.
Yes.
So now we have a proof of concept. We know how to do that. And what I'm hoping is to look at applications either in robotics or in health science of that. So you could imagine building a cast that could react to some solicitation. So that could, for instance, be very stiff in some situation, but give you a little bit of freedom in others. There are people on campus who do artificial muscle. So they have this responsive material, but what we could try to do is design a completely different geometry of a joint, whether it's for implantation, but also simply to build robots or build anything that moves. So yeah, I'm not completely capable of really formulating very concretely what this project is going to look like, but it's going to be about application of these
that principle, basically.
Yeah, these responsive structures. Yeah.
That's very nice. And are there any I guess potential implications of that? I mean, what would that kind of result in if it were applied on a mass scale?
Yeah, there are tons of applications. Actually, last year I saw a talk about nano robots, and so the idea was little structure that could deform and, let's say, capture a small particle or a cell, and this could be controlled by applying a magnetic field.
Wow.
And so the geometry was very naive, and I'm not saying that in a pejorative way.
Yeah.
It's so much work already.
Yeah.
But for this, the geometry of the Leo structure was given. It was simple, what you can think of.
Yeah.
But in a situation like that, I think we can do better. If we're being described what this Leo nano robot should do, we should be able to come up with a much better one. So yeah, tons of again, not really well defined application, but that's the nature of a mathematician. We find problems that are kind of similar, or which in our mind are similar. They can be very, very different, and we try to apply our knowledge to a bunch of different problems.
To a bunch of similar problems, and just use the same sort of framework on them.
Yeah, exactly. Yeah.
That's pretty interesting, and just kind of encapsulating everything of all the work you've done as a researcher, as a I guess someone who teaches a lot of students. What has been some of your, I guess, more prouder accomplishments? over the years in France, Louisiana, and then now in McMaster?
So, I mean, overall, I think people know me for developing what's called the phase field approach to fracture. So
Yes.
I'm proud of that. I think this is something that really has a strong impact. We can predict fracture in some structure or some material in a way that was not possible before. It's been applied to multiple scale from geological structure to cutting glasses, cell phone glasses with laser. There was a project trying to understand why the stones of the dome of the Pantheon in France were fractured in a very specific pattern that used the model that I developed this way. That made me really, really proud.
I can imagine. Yeah.
So from the pure research part, and on the human side, every student who comes through a lab and that kind of discovers themselves, that really reveal themselves as great scientists, are something we're always really, really proud of. Yeah.
Does it feel nice to kind of like see someone at a very early stage in their career as a researcher and then start to kind of take form and begin to really grasp the concepts?
There's always one moment in a kind of a long progression from master's PhD or later where suddenly a student or any researcher starts dominating their problem. I mean, you can really see it is that you switch from teaching something to a student, a postdoc, to at some point, you can see it's like in a matter of days. Then suddenly everything clicks together, and they're the one explaining you what they're doing.
Wow.
So I love this part. And sometimes it takes a really long time, and sometimes it's like from the beginning, but it doesn't matter. That's one of the most satisfying part of supervising students.
It's really beautiful.
Well,
and do you have any tip for any up-and-coming researchers or anyone interested in mathematics? Any piece of advice?
Talk to your faculty, come to class, ask a million questions during classes. First, because it makes our life as professor much more fun. But also it's a good way to attract the attention of people. Try something difficult. And I know that there's a lot of pressure on grades, and especially students who want to go to graduate school feel like they really need to get really, really, really good grades, and A+, straight A+. But that should not be at the expense of taking courses that are challenging and that are difficult. And okay, I don't want to be held responsible if something bad happens because of my advice, but I personally would be much more likely to try to interview and hire a student who had A's and B's and maybe even C's, but have tried some really challenging and high-level courses, rather than seeing somebody has a
straight
A's made of mostly first-year courses and bird courses.
Fair enough. I mean, that's I think that's a very good thing to strive for. Put yourself in an uncomfortable position and actually learn something new that you're interested in. And
but that's really something that is difficult for us faculties. How do we attract students in higher level course in courses where there is a risk of failure, but that's fine. I mean, failure is part of the process. And at the same time, use grades as a
metric.
As a metric, exactly. We have to be consistent with that, and it's difficult.
It would be hard to sieve those people out. I guess if you're going on a purely metric grade scale, you would have to actually talk to them and understand everyone's point of view and where they're coming from.
Exactly. And conversely, if you're a student who will try difficult things. Again, try to get personal connection with your professors.
Yeah.
First, we like it, but also it may turn to be useful at some point.
Yeah. Well, thank you so much. I've learned a lot today. This is I come from a purely biochemistry background. I'm not familiar with much in the way of mathematics, but I've certainly learned a lot today. It's been great chatting with you. And this has been Dr. Blaise Bourdin from the Department of Mathematics. And thank you everyone for listening, and we'll see you next time on Office Hours Unplugged. Thank you.
Thanks for having me.